as I have already said, I'll assume some basic knowledge of string theory, although I may not always use it explicitly. So let me begin by stating the problem that we want to address. So string theory, we know, is a theory of quantum gravity and possibly coupled to also other forces and other particles. However, the main problem in string theory is that intrinsically it is defined in 9+1 space-time dimensions. And the goal of string compactification is to accept that intrinsically space-time is 9+1 dimensional, but look for 9+1 dimensional space-time of the following form. I will write it as R31 times M6, where this you can take to a good approximation as 3+1 dimensional Minkowski space, or if you want to be more careful, it's 3+1 dimensional de Sitter space with a very, very small cosmological constant. And M6 is some compact manifold of small size and when I say small size, small means it has to be sufficiently small so that it's beyond what you can see today experimentally, which is of the order of 10 to the minus 17 centimeter or about a TeV scale. Now the problem, this seems easy, okay, pick some M6 and declare that this is the space-time that we'll be dealing with. The problem, however, of course, is that we cannot choose M6 to be anything that we like. So the theoretical constraint comes from the fact that, so constraints is that this space, either Minkowski times M6 or de Sitter times M6, that this must solve equations of motion of string theory, okay, whatever that may be. So we will make it more specific later. So this is the theoretical constraint. But you also have an experimental constraint, is that the choice of M6 should be such that eventually when you study the theory, which will now look like a 3+1 dimensional theory because M6 has a small size, that theory should look like what you observe in nature. So the effective theory, effective low energy theory, in 3+1 dimension should look like standard model coupled to gravity. So this is the eventual goal of the subject of string compactification. That we first choose, we have to first of all choose a compactification that is sensible, that solves, that is theoretically consistent, and at the same time we will try to look for a compactification that looks like the standard model coupled to gravity at low energy. So it's clear from this that in some sense the subject of string compactification is something that is directly related to what we see experimentally. Okay, this is the closest to the experiment that we can aim for, okay, because we are directly trying to ask the question of how to get the observed universe from string theory. On the other hand, it turns out that this subject is also perhaps the most mathematical part of string theory. And the reasons are, there are many reasons for this. Okay, first of all, this condition is strong that it has to satisfy the equations of motion, but it has many solutions. And then we have to learn first of all that how to decide whether some particular compactification is a solution to the appropriate string equations of motion. And then given that, we have to learn how to extract the low energy physics from the solution. Okay? Suppose somebody gave you some M6 and told you that this is a appropriate, this does solve the string equations of motion. How do you know from that what the low energy physics looks like? Okay? What kind of particles does it have? What kind of interactions does it have, and so on. So this, as we will see, is a complicated mathematical problem in general. Okay? Although we can always construct some simple solutions for this. Okay? And for those it's also easy to work out what the corresponding low energy theory is, except that those solutions don't work. Okay? That they don't describe what we see in nature. Also, in studying this, often we have to go beyond our usual understanding of classical geometry of string theory, or of a general understanding of classical geometry. Okay. So let me explain in a little more detail what I mean by this. Now, as we know, even in 9 plus 1 dimensions, even without talking about compactification, string theory has infinite number of particles. But most of these particles are very, very heavy. Okay. So most states in string theory have large mass, which is typically of the order of 10 to the 19 GeV. Okay, so these are beyond the reach of any present experiment, so you can say that we can ignore them. And so, at least in 9 plus 1 dimension, we focus on the massless states. Massless states. And then hope that eventually these massless states, some of these massless states will acquire mass and give us the kind of particles that we observe in nature. Okay, after all, when you write down the standard model Lagrangian, all the particles are massless anyway. Okay, so the fact that you have to deal with massless states by itself is not a serious problem. Right? So the ninth case will be that you start in 9 plus 1 dimension, we throw away all the massive states and just focus on the massless states. They are described by some kind of 9 plus 1 dimensional quantum field theory. Then we study that 9 plus 1 dimensional quantum field theory on a manifold of this sort. Okay, that will be the ninth case, and that should give us the low energy physics that we are interested in. Now this works in many cases, but this doesn't work in all the cases. And the reason that it doesn't work is that sometimes what may happen is that a particle which was massive in 9 plus 1 dimension, okay, which apparently looked like a massive particle in 9 plus 1 dimension, after compactification can give rise to massless states. So you cannot always first go to the field theory limit in 9 plus 1 dimension and then study that field theory limit on a compact space. Okay, if we could do this, it is still a complicated problem, but it would be a problem in classical geometry. Okay, we take some infinite set of some finite set of fields and analyze the harmonics, various harmonics on a compact space and try to read out what the low energy spectrum will be. But this, while it works in many cases, it doesn't always work. Okay, so you have to be careful. And this is what gives rise to what we normally call stringy geometry. Okay, aspects of geometry which are very surprising from classical geometric viewpoint. Okay, nevertheless, they come out in string theory. A different way of saying this is that in string theory, every particle has a size. Okay? There is no notion of point particle, because anything that you use to probe a geometry is made of strings. Okay? So everything has a size. Okay? And because of this, you cannot really probe a manifold at an arbitrarily small scale. Okay? But the notion of classical geometry is based on the idea that you can probe a manifold to arbitrarily small scale. So because you cannot do that, okay, it is possible in principle for things to happen which will not happen in classical geometry. Okay. For example, in classical geometry or in classical topology, you know the two different manifolds of distinct topology can never be deformed to each other. Okay. But this is something that is possible in string theory. That by continuous change of parameters, you can go from one manifold of a given topology to another manifold of a different topology. Okay. So all this makes this subject also mathematically complicated. Okay, because you have to understand all of these to often appreciate what the low energy physics is. Okay, so we'll begin by ignoring this problem for now and assume that this classical notion of geometry is good enough, namely that we can simply start with the theory of massless states in 9+1 dimension and then compactify on manifolds and study the consequences of that compactification. Yes.
When you say we're focusing on the massless states in the 9+1 dimension,
yes,
that massless sector is derived by quantizing string in flat background.
Exactly. Yes.
But then we are putting it on curved background and see its consequences.
That's right. Yes. Because once you have quantized the point, once you have determined the field theory in a given background, okay, you can always shift. It's like a field theory doesn't change from background to background. Right? What changes is the point around which you expand the theory. Right? You think of, for example, standard model. Right? You have the one Lagrangian. Okay? You can choose to expand it around the maximum of the potential, right, which is a symmetric vacuum, or choose to expand it around the minimum of the potential. So in string theory also, these different choices of this manifold, okay, you can think of as just different classical solutions of some underlying theory. Okay. You determine the underlying theory by working around one particular classical background, and then you can use that underlying theory to study other classical backgrounds. But as you will see, that it's also possible to directly study string theory in these backgrounds, and that will be necessary sometimes, in particular to understand the stringy features of various processes. Okay, so then our first topic will be to low energy limit of string theory in 9+1 dimension. And here we will discuss 5 different theories, because there are apparently 5 different string theories in 9+1 dimensions, although we will see later that they are not really distinct theories. But at this stage we can think as if there are 5 distinct theories in 9+1 dimension, and those are type 2A, 2B, the 2 heterotic theories, E8 plus E8 heterotic, asymptotic to heterotic, and type 1. The other one I should say is that it turns out that for studying compactification, for most analysis but not all, we can just focus on the bosonic sector. Okay, the string theory of course has both massless fermions and massless bosons, and you can write down an effective field theory involving both the bosons and the fermions. But for studying classical solutions, okay, we can pretend that the fermion fields have been set to 0, and we just focus on the bosonic part. Eventually, of course, when we want to determine the spectrum, we want to determine the spectrum of both the bosons and the fermions. Okay, so we start by writing down the low energy limit of type 2 A supergravity. So we focus on the bosonic fields first. And the bosonic fields can be divided into two parts. Okay, although as far as the supergravity is concerned, it doesn't really make a difference, but they arise in string theory in two different ways. One is called the Lebesgue-Schwarz sector, the other one is called Ramon sector. Okay, as I said, for most of what we will be doing, okay, it will not really make a difference that there are these two different sectors. So the Lebesgue-Schwarz sector fields contain the metric G mu nu. It contains a rank 2 antisymmetric tensor field, also called sometimes a two-form field B2 mu nu. This index here refers to the fact that it's a two-form or rank 2 antisymmetric tensor, and the scalar phi is called the dilaton. The Ramon fields include a vector and a three-form rank 3 antisymmetric tensor field C3 mu nu. And we will write down the action involving these fields. Okay, now before I go on, okay, let me just introduce some notations and conventions. Okay. Because since these are antisymmetric forms, antisymmetric fields, we can also use the language of differential form to describe these fields. Okay, and that's often very useful. So I'll just write down the translation between component fields and the differential forms. Okay, what convention we'll be using for describing these. Comes as a tensor.
A small point, this minus 1 to the p, that p has nothing to do with the p form.
No, this is capital P, yes. This is the permutation, okay. So in 3 dimensions, if it's a 3 index object, right, then cyclic permutation doesn't cost any sign, right. 1, 2, 3, 2, 3, 1 and 3, 1, 2, okay, always involve 2 permutations to go from one to the other, right. 1, 2, 3 to 2, 3, 1, right. You have to move 1 through 2 and 3, right. So there it's just cyclic permutation without sign. But if it's even dimensional, right, say take 4 dimensions, 1, 2, 3, 4. 2, 3, 4, 1 will come with an extra minus sign. Right? That's what this minus 1 to the p represents. Okay, because you want this to be totally antisymmetric. And that is guaranteed provided you put this minus 1. Okay, so we are almost there with the conventions. One more thing I have to add, so let me do it here. So in d dimensions, integral of a d form by definition is integral d dx square root of minus determinant g. This is the standard invariant integration method, and then you have to put a scalar. Okay. So that's this curly epsilon mu1 to mu d f d mu1 to mu d. That's what defines this. But now, if you use this formula, fd mu1 to mu d, the idea. No, it's not. It's 1 over d factorial. That's this. Okay. Because 1 over d factorial comes when you define the differential form in terms of fd. You remember there is a 1 over p factorial in the definition, right? Okay, so that 1 over p factorial here is 1 over d factorial. And now you can easily check that this is, because this is totally antisymmetric, this can be written as integral d dx f d 0 1 d minus 1. In other words, this contraction, this is totally antisymmetric, this is totally antisymmetric. So the contraction basically gives you d factorial equal terms. That cancels this 1 over d factorial and gives you this formula over there. So that's the convention for integrating a differential form over a manifold. Yeah, what's important is that this doesn't depend on the metric explicitly. Okay? Because the square root of minus determinant g has cancelled the 1 over square root of minus determinant g that was here in the definition of the same curly epsilon times. Okay, are there any questions?
The convention of metric.
Convention of metric. Metric is minus 1 and then all 1. So you are using that convention. Okay, so in d plus 1 dimension there will be 1 minus sign. But in d dimension 1 minus sign and d minus 1 plus sign. Okay, so let's now go ahead to this theory. Okay. So we define Fp as d Cp minus 1 for p equal to 2 and 4. Okay. We also define f tilde as f tilde 2 by definition is f2, f tilde 4 is f4 minus I define this first. So H3, what is H3? H3 is dB2. This is a 2 form, so the exterior derivative of that is what we will declare as H3. And then f tilde 2 and f tilde 4 are defined this way. Okay, they are defined this way because that's what will enter the action that will write down for the type 2A square derivative. So the action for type 2 supergravity has two pieces. Oh, this is a bosonic action, and then of course there are the formulaic part of the action, which I have not even writing down. These are all bosonic fields. So the term involving the NS sector fields take the following form. The Ramon sector field, SRR. Now I should just say that this 1/12, you could also think of this as half times 1/3 factorial. Okay, this is a standard normalization that we'll be using. Okay. There will always be a factor of half, because after all the kinetic term always comes with a factor of half. And then it will be 1/p factorial if it's a p form field strength whose kinetic term are evaluated. Okay, that's a normalization that is conventionally used. Okay, Ramon field action. So this is again I will write it as 1/2 times 2 factorial.
Double square root and root g.
Oh.
Should there be a minus sign for the kinetic?
Yeah, I think there is a minus sign in front of this one. The other one I have already written. What a minus sign. Now, this kappa 10, this is some constant, but this is not relevant because this can be changed by a shift in the field. So let me explain how that can be done. So here in the NS sector, we can see that if you shift phi by a constant, okay, I just redefine my phi, right? Phi equal to some phi tilde plus constant, that essentially scales kappa 10. That of course doesn't work for the RR sector because there is no e to the minus phi here. But in the RR sector, what you can do is to essentially scale all these RR fields by a constant. You see that this C1 and C3, you look at the definition of F. So F2, suppose you scale these by lambda, okay, C1 and C3. Then F2 and F4 get scaled by lambda. Right? It is just DC. F tilde 2 is just F2, so it gets scaled by lambda. This one involve this gets scaled by lambda and this gets scaled by lambda, right? H doesn't get scaled. This is an SNS sector field. So by scaling the Ramon sector fields, we can scale F tilde, F tilde, F tilde 2 and F tilde 4 by some overall scale. So that you can use to change this. So in this sense, this kappa 10 is a convention dependent constant. Nevertheless, it is useful to fix it, and we will be using the normalization. We will be using the normalization 1 over 2 kappa 10 square as 2 pi over ls to the power 8. What is ls? Ls is 2 pi alpha prime. 2 pi alpha prime is the inverse string tension 1 over the string tension T. Okay. So if you substitute this, you get kappa 10 square or 1 over 2 kappa 10 square, that's the normalization. So 1 over 2 kappa 10 square as 1 over 2 pi to the power 7 ls to the power 8 to alpha prime. Okay, that is the normalization that we will be using, but you should keep in mind that this is just a convention. Okay, because the phi is not fixed for the equation of motion. Any arbitrary phi will solve equations of motion. So this is what we call modular fields. Okay, fields whose scalar fields whose value is not fixed. Okay, it can take any arbitrary value. Okay, so phi is the simplest example of what you will call modulus field in supergravity. Now, it's also more or less clear from the structure of the action that because e to the minus 2 phi comes in front of the action, this constant value of k, if you expand the action around phi equal to k, you will get a e to the minus 2k here over here. And if you compare that with the usual action that we write down, where 1 over g square sits in front of the action, then we consider e to the minus 2k behave as if it's like 1 over g square, the coupling constant square. So e to the k acts as the coupling constant of the theory. Okay. So while string theory doesn't have an intrinsic coupling constant, you can provide a coupling constant in the form of the vacuum expectation value of phi. Small value of e to the phi will correspond to weak coupling, large value of e to the phi will correspond to strong coupling. So it depends on where you are to expand a theory about. Okay, I think now I'll erase the action because we'll probably have said anything that can be said about this. Okay, are there any questions? So let me write here that e to the k is like the coupling constant. Okay, now we have to study the symmetries. in particular gain invariances of this theorem. So first of all, we have general coordinate transformation. That is standard, right? Because you wrote down everything in tensorial form, so it's obviously general coordinate transformation, right? Where these transforms as vector, this is rank tensor and so on. Then we have the gauge invariance of the two form field delta B equal to D lambda by 1. In fact, this is some one form gauge parameter. Okay, this is an invariance. Why? Because H, which is dB, is invariant under this, because exterior derivative squares to 0. And if you remember, the action was written in terms of H. B never appeared explicitly in the form of the action. Then you have the gauge invariance of this delta C1 as d lambda 0. This is 0 form, which means this is a scalar function. This is almost an invariance, but not quite. Why? Because you see, F2, Fp is dCp minus 1. Okay. So F2 is dC1. Okay. C1 changes by dC0, so that's not a problem. Okay. F2 is invariant. So is F4. But F tilde 4, this is what appeared in the action. Okay. F tilde 4 has direct explicitly a C1. Okay. C1 changes by d lambda 0. Okay. So F tilde 4 is not gauge invariant. Okay. However, it's easy to check that we can repair it by also putting a gauge transformation of C3, which is lambda 0 H3. Because in this case, delta of dC3, which is F3, will involve d lambda 0 with H3. Right? D of this, dH3 is 0 anyway, because H3 is dB. Okay, so this is d lambda 0 with H3. So this gives the gauge transformation of F3, and this cancels what will come from the transformation of this. Because dC1 is d lambda 0 with H3, that will cancel this. Okay, so F3. So with this, F4 tilde will go to F4 tilde. Then we also have the gauge invariance of C3 itself, delta C3 equal to d lambda 2. This is also a gauge invariance, because under this F4 is unchanged, and so is F tilde 4. Is this clear? Okay. So to summarize, first of all, the metric associated with the metric, there is general coordinate invariance, okay, and every form field has a gauge invariance, okay, except that the gauge transformation can sometimes be somewhat non-trivial. Okay, that the gauge transformation of a lower form can also act on a higher form field. Okay, just like the gauge transformation of C1 actually affected C3. Okay, this is something to be kept in mind.
Just to clarify, in the third thing, both the transformation are to be taken together, and fourth one is a separate transformation.
Yeah, this is 4 is a separate transformation because lambda 2 is an independent parameter, right? But here it's the same lambda 0 that appears in C1 as well as in C3. Okay, so the final thing I want to do here is to write down the canonical metric. Canonical, yeah, metric and the canonical. Oh, maybe there is something else I should say here. This is a good like to say this. So here you see the C3 has this kind of some anomalous, it's not exactly anomaly in that sense, but somewhat anomalous gauge transformation law because it transforms under the lambda 0. Now one could ask, could you change variables so that C3 didn't transform under this lambda 0 gauge transformation? Is it possible? Maybe we don't use a variable C3 but something else. Could we have changed our variable which is invariant under this lambda 0 gauge transformation? It turns out that is possible by defining C3 prime as C3 prime as C3 plus C1 with B2. Suppose you define it this way. Okay? Then delta C3 prime. Okay, I'll leave it an exercise, it's straightforward exercise. So you can check, becomes something like this: d of lambda 0 with b minus c1 with lambda 1 plus dc1 with lambda 1 and f3 f4 is now, or f4 tilde is now dc3 prime minus f2 with b2. Okay, these are straightforward. I'll just use this new definition and you can show that this is true. Now this part is independently asymmetric, right? Because delta C3 equal to d lambda 2 as a symmetry, right? For any lambda 2. So this part you can find it. This is independently symmetric. So what it is saying is that now if you use the variable C3 prime, then the symmetry, the gauge symmetry, looks like that under delta C3 prime. Now you see that there is no transformation. This is lambda bar. Called it lambda bar, not lambda t, right? So what happens here is that under the lambda 0 gauge transformation, C3 has no transformation. Okay, so the C3 transforms nicely under lambda 0 gauge transformation. But now under the lambda bar 1 gauge transformation, which is the gauge transformation associated with B2, okay, under that now C3 prime transforms. Okay. So C3 prime, you cannot avoid the anomalous transformation of C3 prime, okay, or C3. Okay. It will transform either under the lambda 0 transformation or under the lambda bar 1 transformation anomalously. Okay. But you have a choice of using one or the other. Okay. If you use C3, then it transforms anomalously under lambda 0. If you use C3 prime, then it transforms anomalously under the lambda bar 1 gauge transformation. Is this clear? Okay, but you have a choice of going back and forth. Okay, this will be important later. Okay, when we try to identify fields in different theories.
Don't you have an extra minus sign there? Because when you expand this, the term that say C1 with d lambda bar 1,
Yes.
with a minus sign, it's actually shouldn't that be
See,
plus?
D will, when it goes through C1, it changes sign
Oh, that's
because it's a one form, right?
yeah.
So it will become plus dC1 with d lambda bar 1. So this I'll just leave it as an exercise to check this. Okay, then in terms of C3 prime, you basically have a new anomalous gauge transformation and a new expression for FT level. From this expression, it's clear that C3 prime doesn't have to transform on a lambda 0, right? Because under lambda 0 transformation, F2 is neutral. And C3 prime is also neutral, so there is nothing under lambda 0, this is invariant.
Is it not F4 square and F tilde square? Instead of F tilde square, why is it not F4 square?
Oh, because that's what you find from string theory. Okay. That's the one way of saying this, that the string theory gives you F tilde 4, there is a specific interaction term which is implied by string theory. But at this level, you can also say it's a consequence of supersymmetry. Supersymmetry, in fact, forces you to have F tilde 4 and not F4. Right? But that, I mean, we haven't shown either. Right? But you can derive this, the fact that it's F tilde 4 and not F4, from either of these two principles. One is that you directly look at the string theory, calculate, look at the scattering amplitudes, and see what it implies for this low energy effective field theory. Okay, you will find that there is a F tilde 4. But, or you say that you ask what action is consistent with supersymmetry, and at this level they give the same result. Okay, but there is no option of making it into F4. Okay, so let me say a few words about the fermions. I will not write down the action involving fermions, but only say what the fermions are. Okay. So basically, this is type 2 string theory. So it has, first of all, gravity now. Okay, because this is local supersymmetry, and in fact, this has two gravitational fields in 10 dimensions. Okay. Now, in 10 dimension, you can have Majorana-Weil spinor. Okay, which basically means that you can have spinors with 16 real components, okay, which are also chiral. Okay. So the gravity knows psi mu I equal to 1, 2. Okay. So mu, of course, is a vector index. I have not written here the spinor index. Spinor index takes 16 values. Okay, these are real spinor fields. Okay. So type 2 theory has two of these. Okay, so how many components? 10 times 16. Each of them have, because mu takes 10 values, okay, 10 times 16 components, and I takes values 1 and 2. Okay. The important point is that these have opposite chirality. So psi mu 1 and psi mu 2 have opposite chirality. So one is left-handed, the other one is right-handed. Besides this, it also has two other spinor fields, okay, the dilatinos, okay, which are also Majorana-Weil, and again chi 1 and chi 2 have opposite chirality. Okay, this is what you get from string theory, okay, or type 2 supergravity. And we can write down the action involving the fermionic fields as well. Okay, again you can either use string theory or you can use supergravity, the supersymmetry, to write down the action, but I will not write it down explicitly. So this is what is normally called n equal to 2 supersymmetry in 10 dimensions. Okay, because it has two gravity laws. So there are two distinct supersymmetric transformation parameters. Okay, epsilon 1 and epsilon 2. One transforms the first gravity law, the second one transforms the second gravity law. So n equal to 2 supersymmetry. Okay, so let me now turn to type 2b. And here I will try to be quick because it's very similar to what we already saw in type 2a. Few changes.
Sir,
Yes.
so if we look at it from string point of view,
Yes.
then we say that we are naturally arising at n equals to supersymmetry in 10 dimensions.
In type 2 theories,
Yes. Sir. But if we look at it from just field theory point of view, so why is it that I'm writing maximal thing? I mean.
No, there is nothing. String theory gives you this maximal supersymmetry.
Yes, sir, but if you look it from the string point of view, but suppose I want to do some field theory in 10 dimensions and with
You can write down any theory that you like,
Yes,
right?
sir.
Except that it will not be renormalizable,
Yes.
right? So if I write classically, you can write down any field theory that you like,
Yes,
right?
sir.
You will not any supersymmetry,
Mhm.
right? It will not be a good quantum theory because you don't know how to quantize it.
Yes, sir. So, but yeah, so n equals 2 will perhaps be maximal supersymmetry.
Yes, n equal to 2 is maximal.
So, my question is why not just if we are looking it from field theory point of view, why not just n equals 1?
Yes, you can write down n equal to 1 theories, and in fact, two heterotic string theories,
Okay, so
both have n equal to 1 supersymmetry. But what I'm saying, not every n equal to 1 supersymmetric theory in 10 dimension will have good ultraviolet property.
okay.
Right? So supersymmetry doesn't guarantee that it's ultraviolet finite, or even if it's renormalizable. Right? You really need string theory to ensure that you have a finite, ultraviolet finite theory. Right? But then when you do analysis of the kind we are doing, string compactification, right? Often you can ignore these heavy string states, right? And think in terms of supergravity. Okay? But without having an underlying string theory, right, you cannot really make sense of the theory because it's ultraviolet divergent. Right? So that's the role of string theory in this analysis. And as I said, string theory also has other roles, even in the context of compactification, because sometimes it gives surprises, right? You get extra massless states that you wouldn't see from a field theory. If we had started with the field theory in 10 dimension and done the compactification, then you wouldn't see the extra states, but string theory gives you extra light states. Okay, but those are spatial. Okay? But in general, right, without having an underlying string theory, you cannot really make sense of the theory because of the ultraviolet divergence. Yeah, so that's the main reason why we want to have string theory. Okay, are there any other questions? Okay, so 2b, again we have NSNS and our NSNS sector in fact is identical. So this has again G mu nu phi, but RR sector now has different kinds of fields. It has a zero form scalar C2 and C4. So we again define our F's. F1 is DC1, F3, sorry, DC0, F3, okay. F's are just directly D's. Okay, so F4 or F5 is DC4. But F tilde, which appear in the action, F tilde 1 is the same as F1. F tilde 3 is F3 minus C0 wedge H3, and F tilde 5 5 minus half C2 wedge H3 plus half D2 wedge H3. Okay, I have written it in a very specific form for reasons that will explain later. But again, by defining C3 prime and C4, C2 prime and C4 prime in the way we did earlier, okay, we can shift these coefficients around. Okay, it's exactly the same as what we did earlier. Okay, for example, instead of having two terms, okay, by appropriate shift, okay, appropriate redefinition, okay, of C4 prime, you can just keep one of the two terms, okay, but the coefficient will change. Okay. We have kept it this way so that it looks more symmetric between C2 and B2. Okay, for reasons will be explained later. So the action is again a sum of two terms, NS sector terms, and then RR. This is identical to type 2. So I will not type it down. This of course is new because RR fields are new. So yes, RR is minus 1 over 2 kappa 10 square. In fact, once I have defined these F tilde fields, it's quite standard, right? You can just write it down by inscription. Okay, it's the square of each of these field strengths, right? Field strengths. So half G mu nu F1 mu F1 mu. F1 mu is a fancy way of writing partial mu of C0. Right? It's just a derivative of the scalar field. Plus 1 over 2 times 3 factorial, again minus sign is there, 1 over 2 times 3 factorial, G mu prime G mu prime G rho prime F tilde 3 mu rho F tilde 3 mu prime rho prime. Okay, so this is the action of type 2B supergravity, which comes as the low energy limit of type 2B string theory. But there is a condition, additional constraint, which is that this field strength has to be self-dual. So now I am going to introduce another notation, star F5. As I say, it's not, you cannot derive this condition by the extremization principle. Okay? That is the statement. If we want to minimize something that is manifestly Lorentz invariant, right, or manifestly general coordinate invariant in this case.
this condition we want to put on the equation of motion or overall?
On the equation, meaning after you derive the equation of motion, you have to impose this condition,
Yes.
right? Which, if you translate to S matrix, right? What it means is that you can use this to calculate S matrix, but then the external states have to be restricted according to this constraint. Right? So in this sense, you can use this action for calculating S matrix, but this action allows for more external physical states than what you really have in the theory. Okay, and that constraint on the external states is imposed by this.
So this is an additional on-shell condition.
Exactly, this is an additional on-shell condition.
So if I perform a path integral, then in the off-shell fields I do not impose this. It's only
No, you have to impose this off-shell. So this is classical, right? So if you look at the point, you don't quantize this action, right? You quantize type to be string theory, which has different set of rules altogether. There, if you look at what states propagate in the intermediate, what states are propagating in the loop, it's always states satisfying this condition. Okay, so in this sense, you don't allow off-shell fields also to violate this. Okay, because they all propagate, they don't propagate in the loop either. Okay. So that's the reason. So as far as the classical action is concerned, right, there is nothing, bad about this, because you just use this to derive the classical equations of motion and then you impose this condition. Right? This action is not good for quantizing the theory. Right? Now that way, of course, type 2 action is also not good for quantizing the theory, right? Because of the ultraviolet divergence. So you really have to use string theory. So from that perspective, right, it's not any worse than what you have in type 2A string theory, because for both, to quantize it, you have to go to string theory.
But I guess there is a formalism to use an infinite number of auxiliary fields.
Yes, if you are willing to use infinite number of auxiliary fields, you may be able to get there. Right? But even then, for example, in string field theory, I don't think there is any way to write down a string field theory, right, with all the required properties, which gives you this. Right? You can write down the equation of motion for a string field theory, but not a string field theory action. So you have to, the auxiliary fields that you have to introduce, right, will be more than what you naturally get from string field theory, for example. Okay, so let me maybe also write down the canonical metric. So canonical metric, the transformation is exactly the same. So if write G mu nu as e to the pi by 2, then G mu nu, and then substitute and derive the action. So the NS is the same. This is the same as 2. The Ramon part is slightly different because you pick up different factors of e to the phi in different terms. Okay, so let me write that. Anyway, so Ramon is minus 1 over 2 square. So this is what you get. Ramon. Now, here you notice that there are now two modulus fields. Phi of course is modulus, phi has no potential still. But C0, which is another scalar, is also a modulus. Okay, it has no potential. So, a generic solution can be G mu nu equal to eta mu nu, phi is an arbitrary constant, C0 is an arbitrary constant. So, phi and C0 are modulus. It turns out that we can make this, bring this whole action in a much more symmetric form by introducing a couple of redefinitions. So we define tau as C0 plus I e to the minus phi, and G3 as the 3 form, which is F3 minus tau H3. So G3 is complex because tau is a complex variable. Okay, tau is a complex field, so G3 is F3 minus tau H3. That's the definition. These are this definition. Okay. And I'll leave as an exercise to show that now the type 2B action takes the following form. So imaginary part of tau is basically this e to the minus phi. Actually, in fact, I had forgotten to write one term in the action, which I will write now. If this term was there from the beginning, I didn't write up there. Okay, let me write here. Here, minus 1 over 4 kappa 10 square here also. So what this means is the following. This you can see is a 10 form, right? 4 plus 3 plus 3, that's a 10 form. And we had described earlier what we mean by integrating a D form in a D-dimensional manifold. Right? You take the components, multiply by the contract with the epsilon tensor, with 1 over D factorial, and then integrate it. Okay, that's what this term means. Is this okay? This I'll leave as an exercise. And then there is even one more complicated exercise. So SL2R basically means that we have the condition that AD minus BC equal to 1 on this matrix. Okay, so then we also transform the two form fields B2 and C2 goes to BCE A times C2. C4 remains unchanged and G0 remains unchanged. Okay, this is straightforward. What you have to do is to check that the action is met. For example, this part, this term, the kinetic term for tau. Okay, it's not hard to see that this is invariant under that transformation. Okay. In fact, you can make life simple by noting that basically to prove this, it's generated by two independent transformations, because you can combine the two independent transformations to generate others. One is shift in tau, tau goes to tau plus 1, or two strongly coupled theory. Okay. And at present, we only know how to study string theory at weak coupling, okay, as a perturbation expansion. Okay, and that is the reason why we cannot say for sure that this is a symmetry of a theory. Okay, there are many indirect evidences that indeed this is a symmetry of a theory. Okay, and we will proceed with the assumption that this is a symmetry of a theory. Okay, even though this has not been proven. Okay, what we can do at best is that we can work out various consequences of this symmetry. Okay, and those consequences have been tested in many different situations.
These are non-perturbative check.
These are non-perturbative checks. Yes, exactly. No perturbative check is possible, right? Because perturbation expansion is an expansion in parts of GS, the G string, right? And we are talking about a symmetry which takes G string to 1 over G string. So obviously the perturbation series in G string and perturbation series in 1 over G string you cannot compare. So you have to go beyond perturbation theory, and there are some non-perturbative information you have in string theory, and those are the ones that are used to test this symmetry. Okay, so I think I will stop here. So next time we will start with the rest of the supergravity which will be relevant for us, namely the type 1 theory, the SO32 and 8 cross 8 heterotic string theory, okay, and also a theory in 11 dimensions, okay, which is the 11 dimensional supergravity. And then once you understand all the starting points, the supergravities in 10 or 11 dimensions, then we will start by compactifying and see what we can study, what we can learn from there. Okay, so we'll continue tomorrow.
in we know type 2A and 2B theory are trivial to each other. So given that, so should not they have same number of modularities as well? Here we
That is
have
after compactification. After compactification on a circle, yes, they will have the same number of moduli fields. See, type 2 and type 2B are trivial only after compactification, right?
Yes.
So after compactifying, they will have the same number of moduli fields, but not in 10 dimensions. So we will study type 2 and type 2B on compactifying circles and see what we get there.